Hi, Dr. Taverton. How are you?
I'm great. Wondering if the traffic in Texas is bad today.
I'm sorry, the traffic what?
I was wondering if the traffic in Texas was bad today, in terms of you getting there on time.
Well, actually I was preparing some material about Florence. Because there's a hurricane coming up on the, oh my goodness, I didn't link it.
Yeah, I guess I've just heard that Renzi's going to be going into sort of emergency mode with their supercomputer center there, and keeping the control room cool so that they can run the models they need to.
So I prepared some stuff, but I didn't link it to the web page, so I don't think I can get access to it now. Never mind, I'll just wing it. So you've probably heard on the news that Hurricane Florence is heading towards the Carolinas, and so that's bringing up again what can be anticipated about the impact of hurricanes ahead of time. So I started looking into this a little bit. It's not quite the same as our subject for today, but it's a topical subject, especially for those people who are in the pathway of the hurricane, which is basically headed towards North Carolina now. So today we're going to talk about geodesy and map projections and coordinate systems, but I thought, given the nature of the circumstances here, it would be useful to take a look at what's happening. So at the National Hurricane Center, there's forecasts here. This is for Florence. So this is the forecast as of today at 11 o'clock, and it's scheduled to arrive on the Carolina coast at 8 a.m. on Friday. And I guess M, I'm not sure what M means here. And anyway, and then to go inland, and you can see this pathway out here. And so if you go to water.noaa.map water.noaa.gov/map, that brings you to something that says you've got to pledge your firstborn child and all that kind of thing. And this is a map of the flow, the forecast flow across the country. So if you come into the Carolinas here, and we're going, and you can see that these are the main impacted areas are going to be in here, in this region of North Carolina, and actually north here in Virginia. And there's a set of anomaly maps here that are actually quite interesting. So if you say stream flow anomaly, what that means is it high or low relative to the normal flow, and this is the medium range forecast, which is 10 days ahead. Now if you look at the Carolinas now and sort of focus in, you can see it's all red right now, so there's nothing really too much going on there. So this is going to truck along for a while, and you can see that there's actually, the red colour means low flows and the black colour means high flows. So this is now 14th, the 15th, and it doesn't, you have to wait till it, let me see if I can just advance this a bit. So 16th. Now, you can see this starting to get dark here. So this is where the hurricane is coming ashore on the 17th. So this is about 6 days out from now. And see how this is all going dark here? This is where the hurricane's penetrating up into Virginia and going further north here. So all this black area here is the impact of Florence. And as it goes along, this is now the 19th, and so on. And you can see actually there was I think the state of South Carolina has evacuated the whole coast. But it looks from this that the impact is going to be in North Carolina and in Virginia. And so you can see, now here it is, this is the 11th against this, back to the beginning. So this is the forecasting that's coming from the medium range version of the National Water Model. It's a 10 days ahead outlook that's being constructed and is consistent with the images that are coming from the National Hurricane Center. So, yeah, it's, having been through Harvey, I'm conscious of what these people in North Carolina are going to be facing shortly. Okay, so last Thursday we had exercise 1. You guys okay with exercise 1? Yeah. Don't feel like you've got to do exactly the map, the one that I created in the exercise. Or that your chart has to be exactly the same. The point is not to be exactly the same. The point is just to be able to make a map and make a chart and do something decent. So don't feel like, oh, it's got to be exactly like what you say. Yes?
For that histogram that we're turning in, are you supposed to include that little like this snipping tool snapshot up in the corner, or is that just extra?
The histogram, snipping shot, map tool. I'm not quite sure.
It's one of the things that we turn in, and you're talking about how to save images. And there's the one where you save it as a TIFF, but then you're talking about using this snipping tool.
Oh, no, so the idea about using the snipping tool is just a helpful tip, right? So when we make up these exercises, there's lots of maps and charts and things in them, and we do them with snipping all the time. And the option of taking the layout and exporting as a TIFF, or taking the map and exporting it as a TIFF, is a more sort of sophisticated way of doing it. And so in this instance, I wanted you to be aware of that, but for kind of the quickie version, the snip is easier and quicker. And but in this instance, we don't need that as well. Yes?
And one of the deliverables, it says that we should submit a monthly chart for like the layout one, but then at the bottom of the PDF it says, it doesn't say anything about monthly, so should we follow the monthly or should we follow?
So what I had in mind when giving that, well, let me just get it out of the... So near the end here, there's a bar chart. There. This is what I had in mind. Something like this. Is that what you mean?
Yeah, for like the instructions beneath it. So it says like monthly. So is that the layout one? Yeah.
So prepare an ArcMap chart coupled with a graph showing monthly evaporation plotted from the gauges. Ah, that's a good question. Let's just say with a graph showing evaporation data plotted from the gauges. Yeah, don't worry about the word monthly. Yeah, okay. So, yeah, just ignore the word monthly. I'm sorry that there's a... What I had in mind was something like this, but really the reality is that I don't really mind how you do this. I just want to have a map and a chart and the whole thing turned in as one connected set. Whether it's the monthly chart or whether it's an annual chart or what kind of a chart it is isn't really the point. The point of this is to say that things vary in space and they vary in time, and we wanted to get a sense of that. Any other questions about the homework? Dr. Tarberton, do you have any thoughts?
So, I mean, I guess I've had the question about the monthly as well, and I've said that to possibly include two charts, something like the chart that you've got on the screen as well as the monthly one below, and if possible to put more than one station on it, because sometimes there's a way to have multiple bars. But I mean, I think in general the idea of just telling an interesting story about what you've learned with the data is what I would be looking for. And part of that interesting story is making sure that what you show is complete and speaks for itself. So if you put something like evaporation on the y-axis, label it with units like inches. Don't just say evaporation and numbers going from 0 to 12, because then we have no idea what they are. If you've got, make it, give the titles and captions and other sort of ancillary information, try and make it sufficient so that somebody can understand it. And that's why I sometimes want to say, if you show maps, show me where north is. I mean, it's not always up. So put a north arrow. Show me a scale so that I know whether it's what a mile is. Things like that.
Yeah, when I made this original map, and this is one we did several years ago, I took this chart in Excel and then I put the screen capture out of ArcMap into it, just to show that you could do the reverse, right? That maps could inform charts just as charts inform maps. That was the intention of this idea here. But yeah, I'm just, as Dr. Tubman says, the point of this is just to get you so that you can express information about maps and charts and do it in a connected way. And don't be too locked into exactly what we say, just replicating what's in the exercise here. Any other questions? Okay, so let's continue on then. I know you've been anxiously following events at the Oval. Yes? England playing India at the Oval, yes. Haris has been anxiously following the Oval. There was a great fourth innings stand between KL Rahul and Pant, who's the Indian wicketkeeper, of over 200 runs, and it seemed for a while that India might make a huge total sufficient to defeat England, but unfortunately they ran out of gas right at the end. And so England won the fifth test at the Oval. So I know you were all excited about that and were following along. I personally have been to the Oval, which is a cricket ground in the suburbs of London. So it's one of the great sights. I was there in 1976, and when I was 26 years old, I saw Viv Richards get 287 runs for the West Indies against England. Wonderful batsman. I mean, you can imagine, he started on about 11 o'clock on the first morning and he was out at tea on the second day. The cricket tests take 5 days, so this is not a quick job. Okay, so we're going to talk about geodesy, map projections and coordinate systems. And this is a lecture that I always enjoy giving. When I first started working on GIS, I didn't know much about this work, and so my wife was training as a kidney specialist at Stanford University Hospital, and I holed up in the Earth Sciences Library at Stanford and just read for 3 months. I read all the books I could find about this subject, and at the end I was better informed than I was at the beginning. So geodesy, the shape of the Earth and the definition of Earth datums, map projection, the transformation of a curved Earth onto a flat map, and coordinate systems that deal with how you get X, Y and Z coordinates for map data. And there's some readings here that come from the ArcGIS help system. So this is one area where there's actually substantial readings in the help system that are pretty informative. The ones up the top have nice charts and explanations in them, and I think you'll find those useful. I also wrote a fairly long synopsis for this and passed it out yesterday so that you could see more about what's going on. So there's some discussion about learning objectives here. That we're going to come back to this several times about distances and doing calculations and so on. We're going to give you a homework after class or for class next time about this. So there's a reading here on map projections, about what are map projections. When you go to these readings that says what's a coordinate system and so on, go down from the screen that they're sort of like one screen at a time. Go down several screens so that you can see the subsequent information that's there, not just at the top end. When you go to work with ArcGIS, we're going to be working with a geodatabase, an exercise 2 with a little thing there with the square boxes called, it's called a feature data set. and that has certain properties. In this case, it's the geographic coordinate system of North America. And so what we want to do today is to understand what all those things mean. So there are various kinds of horizontal coordinate systems. In other words, coordinate systems that express things in latitude and longitude or in easting and northing. And we're going to be dealing with the North American datum of 1983, an earlier version called the North American datum of 1927, and the World Geodetic System of 1984. Those are the three main shapes of the Earth or Earth orientations that we're going to be dealing with. For projected coordinate systems, or on a flat page, we'll be dealing with Alber's equal area projection, transverse Mercator, probably some other projections too, but those are the key ones. So what's happened in surveying? Probably you're aware of this, but traditionally surveying was done with instruments, and well, perhaps not quite as precarious as you see here, and with benchmarks. And all around our campus, if you look around on the sidewalks, you'll find benchmarks embedded in the sidewalks of our campus. We've got about 20 or 30 benchmarks that are embedded that show where things are and where buildings are relative to the benchmarks and so on. What's happening now is something else called CORES, which stands for Continuously Operating Reference System. And these are GPS units that are held in fixed positions. And so they're actually continuously operating, they're continuously measuring location with respect to satellites, and this CORES network is the key thing for GPS navigation. These are various kinds of global positioning system instruments, and of course we're all familiar with this now because effectively you have this in your phone. And it's interesting to understand how this works. So actually in GPS there are 24 satellites up circulating the Earth all the time, and they're oriented such that you try to find at least 4 that you can see from any particular place. And the idea of this is that radio waves proceed at the speed of light, and so the GPS satellite sends out a signal, and then when it's received at the ground, there's a time lag between the time that the signal was sent and the time that the signal was received. And it's embedded, the time that the signal was sent was embedded in the signal, so when your receiver, and that includes your phone, gets the signal, it knows how long it was since it was sent, and that's how it knows how far away the satellite is. So just by distance measurement is how it happens. And so if you think about, if I can see one satellite, then I know that the distance measured that says R, that's a sphere. And if I take 2 satellites and know where I am, if you take the intersection of 2 spheres, you get what? And you get something, right? Intersection of 2 spheres is a circle. The intersection of 2 spheres is a circle. So you know you're somewhere on a circle if you can see 2 satellites. If you can see 3 satellites, then you've got the intersection of 2 circles, which means you've got, in this case, 2 points. And if you can see 4 satellites, bingo, you're there. So these systems work on the basis of distance measurement, and you have to see 4 to really be precise about where you are. Now there's a term here called differential GPS, and what that means is that the errors in the GPS instruments are being tracked all the time, and errors come from the content of the atmosphere, which impedes the signal that comes from the satellites, and so it's now possible to measure something accurately within 1 centimeter horizontally and 2 centimeters vertically in 3 minutes. And when you think about that, that is an amazing accomplishment. The technology can now tell you where you are. And if you leave the instrument in place longer, the result gets more and more precise. Now, this has to take tectonic motions into account. So where are we going to now? You're standing in this building. Where are we heading? Excuse me? West. We're heading west. Yes, we're going to Arizona. So this building is on its way to Arizona. And it's going west because it's sitting on the North American plate. It's about 6 millimeters a year. So in other words, if we set a GPS unit on the top of this building, it is visibly moving. I mean, it's moving at a perceptible, measurable rate. And you think, how can that even be possible, right? Our building is going like this, yeah? We are going like this as well, right? So we're moving. You can see that the Pacific plate is moving in a completely different direction, and so the intersection of the Pacific plate and the North American plate is the big cause for earthquakes in California on the San Andreas Fault. You can see Australia's heading off to the northeast real fast, and other places on Earth are going around at relatively larger or smaller speeds. And so horizontal tectonic motions, the ones that are applicable for us, are shown in this picture. When is California not in North America? It's when it's on the Pacific plate. So California, you know, it's in some other place. What can you say? It's California. But that's why there's all the crazy people there. But anyway, so much for that. This is important, as you can imagine. If you say, where are we? You know, where are we is not a static question, actually. Where are we is a dynamic question. In New Zealand, they have a so-called dynamic datum. So the official position of something was where it was on the 1st of January 2000. So they go back in time and say, you know, wherever that thing was is like that's where it really is. So there's a series of benchmarks, and we have them here on campus that are survey benchmarks that have latitude, longitude, and elevation associated with them. And as the Earth is moving all around, you have to make adjustments of this. And so this is a slide that I got from the National Geodetic Survey, and it shows the density of the survey benchmarks, and the yellow dots here are the stations that are used in making adjustments of that. And you can see that the density varies by state. A lot of this work's done by state geodetic surveys. South Carolina, for example, is a very active state. And so the question of then what is latitude, what is longitude, and so on has to be a carefully considered question. So we're going to go into a little bit of definitions here. So the latitude and longitude are defined using an ellipsoid, which is an ellipse rotated around an axis. But the elevation is defined using a geoid, which is a surface of constant gravitational potential. What does that mean, constant gravitational potential? What's Newton's law of gravitation? Oh, F equals mg. I mean, it seems like, yeah, we've got some engineers here. Yeah. So a surface of constant gravitational potential means that the g in the F equals mg is a constant. It's a constant value. For a given mass, then you've got a certain force. And datums define standard values of the ellipsoid and the geoid. Now you may think, what is g? G is 9.8 meters per second squared. Well, no, it turns out g is kind of a fuzzy thing. It's not, we've treated it as a specific number, but it's actually a variable. So we think of the Earth as a sphere, but it's really a spheroid, which is slightly larger in radius at the equator than at the poles. And this ellipse then is defined by the focal distance, in other words, this little epsilon here, of where the focal points of the ellipse depart from the center. If those two points come together, then we have a circle, or a spherical Earth. So for the Earth as it is, the major axis is about 6,378 kilometers, and the minor axis is 6,357 kilometers, and that means that there's a flattening ratio of about 1 in 300. In other words, you've got 299 up this way and 300 this way. So if you rotate that around, then the ellipse becomes an ellipsoid or a spheroid. And these are the statistics of the two major spheroids that have been used in mapping the United States. There was so-called Clark 1866 ellipsoid that was developed by a British geotechnical engineer, and then this GRS 80 is the one that's the main one now. And the difference between them is that the global reference system of 1980 was done from satellites. So satellite measurements from satellites made a revolution really in how to shape the Earth. So the two systems that for defining the shape of the Earth that are in active use are the World Geodetic System. It's a global system for defining latitude and longitude on the Earth independent of tectonic movement. So The WGS doesn't worry about all these plate movements and so on, and it's a military system. And the Google Maps reference that you're working with in exercise 1 where you get to the end and it says, oh, we've got to make these maps so they're like Google Maps, that uses the WGS-84 system. Now, the North American datum is a system defined for fixed objects on the Earth's surface, and it includes tectonic movement. So the idea is it's okay if the North American plate's going to California. It's the relative location on there that matters. So we've got an ellipse and an axis of rotation that define a horizontal Earth datum. The NAD-27, North American datum of 1927, uses the Clark 1866 ellipsoid on a non-geocentric axis of rotation. And what that means is that in the 1920s they decided Canada, United States and Mexico would make a surface of the Earth that was oriented as best as possible to make maps for this area. And so they didn't worry about what was going on in China and whatever else is on the other side of the Earth. They made a surface of the Earth that was as close to the Earth's surface as they could. And actually there's a centre of it in Meads Range in Kansas or somewhere that's the point that actually is the location of that datum. Then when satellites became used for measuring the Earth, it became clear that it was better to do this on a geocentric axis of rotation. In other words, that the axis of rotation goes through the poles. The North American datum of 1927 does not. It's kind of kinked so that the surface of the Earth is close to the geoid in North America. And the WGS-84 is nearly the same as NAD-83, and I'll show a comparison between them. Now this has some significance because when you look up the geographic coverages that you can, or geographic projections you can use, you get these kinds of options. And you look at this and your eyes sort of glaze over and you go, oh, I don't even know what all that means. Well, probably you don't need to worry about that. Whenever I look at all these things, I just go to NAD-83 and don't worry about the rest. But these other CORS 96 and CSRS is a Canadian system. NSRS means National Spatial Reference System, and HARN means High Accuracy Reference Network. These are progressively smaller refinements on the geoid and the ellipsoid that have been done since NAD-83 was defined. So when you think about the Earth, we've got this ellipsoid, this geometrically precise thing, and then we've got the real surface of the Earth, which is sort of a bumpy thing. It has mountains and all this kind of stuff. And then we have the geoid. And the geoid is the surface of constant gravitational potential. For decades, I used to talk about mean sea level and say that was the same thing as the geoid, but it turns out that I was wrong. There is no such thing as mean sea level. The sea's rising, and it turns out the sea surface has topography. It's kind of a fuzzy thing. But anyway, the geoid is the surface of constant gravitational potential, and if you take the Earth and look at the location of the centre of the Earth, then what you find for the NAD-83 and NAD-27 ellipsoids is that they differ in distance at the centre of the Earth by about 200 metres, and that has some significance about where things are at the top of the Earth. If you compare the WGS-84 and NAD-83 data, you find they differ by only about 2 metres at the centre of the Earth. So that's a very small difference actually compared with NAD-27. Now, if we define latitude, it turns out the definition is sort of complicated, because if we take a point on the Earth, then what we do is take a tangent plane to that point on the Earth, then a perpendicular to the tangent plane, and where the perpendicular to the tangent plane intersects the equatorial plane, that angle, phi, is the latitude of that point. That's not to do with the centre of the Earth, it's this the angle that the normal to the tangent plane makes with the equatorial plane. For meridians it's a bit easier. There's just the idea that there's a cutting plane that goes through the Earth and through the polar axis at a certain orientation, and that cutting plane defines a meridian as it goes around the Earth. And this is a chart that I made of just looking down on the Earth from the North Pole. And so the standard meridian, 0 east and west, is here. It goes through Britain. And so at any particular rotation from that, you get a another meridian. In this case, there's a location P here, which is at minus 30 degrees, which means 30 degrees west. You have to get sort of out in the Atlantic Ocean there somewhere. And so the latitude is just defined as the angle between two cutting planes. It's a simpler concept if you want to consider latitude and longitude on a sphere. So you can do rotation from the prime meridian and elevation from the equator. That gives latitude and longitude that are simply accessed. Rather, the spheroid is a lot more complicated. So this is a particularly important concept here because we're going to ask you questions about this. So when you think about distance, so in the exercise that you're just doing, I asked you to say how wide is Texas from east to west and how long is it from north to south. Now it turns out that distances from north to south are always calculated by a constant formula. In other words, a distance AB here is just RE, the Earth radius, times del phi. In other words, the angle of the angle subtended by the distance AB at the Earth's center. And the del phi is just arc equals r theta. If you take this as a, sorry, I'm assuming here that the Earth is a sphere. However, if you take the distance CD, when you're coming up in latitude and then you're rotating, you've got now this other quantity here, cosine of phi, that comes into the equation that just says that the distance along a parallel is diminishing as you go away from the equator. And that's because the parallels come together. Sorry, the meridians come together. That means that the distance between them along a parallel gets shorter and shorter. And this, if you remember the ice skaters in the Olympics, when they're out like this and their arms are out and they're spinning slowly and then they go like this, and they go round and round fast. Well, that's the same thing as what happens when air is passing over the Earth. When it comes to the north and it's spinning, it starts spinning faster because this basically the radius of distance here becomes smaller as you go towards the poles. So this is an example of a calculation that takes this into account. So if we say what's the length of a 1 degree increment on a meridian and on a parallel at 30 degrees north and 90 degrees west, assuming a spherical Earth with a radius of 6,370 kilometers, firstly you have to convert the angle to radians because radians is the non-dimensional measure of angle. So it's 0.0175 radians, then multiply by the Earth radius and you get that vertically it's 111 kilometers. Whereas horizontally along the parallel it's the same distance but times cosine of 30. What's the cosine of 30? You wake up in the morning and say, it's the sine of 30. 0.5 is the sine of 30. Cosine is
Square root of 3 over 2.
0.8660. Yes. You should. I mean, you wake up in the morning and think, cosine of 30, 0.8660. Yeah. Sine of 60. Yeah. Yeah. Now, a more sophisticated equation is presented here for what's called the Great Circle. So if you just take two arbitrary points on the Earth and say, I want to find the distance between them, then this much more complicated formula comes into play. To calculate that formula is a pain. Even with Excel, it's a pain. So I want you to be aware that such a formula exists, but it's a pain to calculate it. It's a lot easier to do it the way that we're going to ask you to actually, in the next homework exercise, to do this using great circle distances with ArcGIS. But who was the person who followed the Great Circle route across the Earth in 1927? Who's that? Lindbergh, yes, Charles Lindbergh. So Charles Lindbergh, the Lone Eagle, flew from New York to Paris on the Great Circle route. So once he plotted in 100-mile lengths what the Great Circle route was, the shortest distance between New York and Paris. And he flew across the Atlantic Ocean and through the night. And when it came light again, he went across Ireland and Dingle Bay, about 3 miles off his path. It was just an amazing piece of navigation. Now, when you say how high is something, Turns out that's a complicated question, and that there are three different ways to measure elevation. You can think of them as like three rulers. One of them is to use land surveying, and these are called orthometric heights, and they measure height above the geoid. The second version is called ellipsoidal heights, and these are heights above the ellipsoid, and this is what GPS works on. And because GPS has become so ubiquitous, even though orthometric heights are the legal standard, this is now becoming a dominant measure of how elevation is measured. And finally, there are tidal heights, like how high is high tide or mean tide, low tide, and so on. And so the conversion among all these systems is a complicated quantity. One of the things that was really instructive to me, about 10 years ago I was involved in a National Academy study of flooding across the country, and we were looking at these questions about geoids and ellipsoids and all this kind of stuff and trying to figure all this out. And we came across these tidal records. So this is the tide in Charleston, South Carolina. This is the tide in Galveston, Texas. This is the tide in Juneau, Alaska, over a period of about 100 years. And you can see there are just remarkable gradients here that cannot be explained away. And why is Galveston, Texas about twice Charleston, South Carolina? It's because of deposition. So Galveston is still geologically settling. It's that there was a sediment from the Trinity River. So that in Galveston, the land is going down and the sea is going up. In Charleston, the average around the US coast is about a foot a century. Now you can say, Juneau, what's going on in Juneau? Juneau's being lifted up because of Earth tectonic movements. And so the sea's actually receding from Juneau. So the whole question about what is a tide and what is mean sea level doesn't make any sense anymore. These trends in the overall that the sea is rising, and it's rising because it's expanding. It's absorbing the energy from a heated atmosphere and mixing it down into the ocean, and the ocean is expanding. And that's why about 90% of all the energy that's being created because of the greenhouse effect is being stored in the oceans. And that's why the sea level is rising. So we've got these three quantities then, the geoid, the ellipsoid, and the Earth's surface. And the difference between the geoid and the ellipsoid is called the gravity anomaly. In other words, how much does a surface of constant gravitational potential differ from a surface that's just drawn geometrically? And the formal definition of elevation is that it is the height above the geoid. In other words, it's defined in this gravimetric way, the elevation above the surface of constant gravitational potential. Now, we have here at UT the science development for this experiment. It was actually proposed by a colleague here on the faculty called GRACE, which stands for Gravity Recovery and Climate Experiment. And there were these two satellites that were initially launched in 2002. It's supposed to last for 3 years, and it's kept on going all these years. They can only got the power on for part of the year now, but a new mission is being launched to replace this one, I think, either this year, perhaps it's even been launched. But the idea was that you have these two satellites, and they're 220 kilometers apart, and you can measure the distance between them to 2 microns. And so as they fly around the Earth, as the Earth pulls them in, the distance diminishes slightly where the gravity is greater, and when it's less, they come apart. And so from that, you can make this map of this sort of lumpy Earth where the gravity is greater and where the gravity is less. It turns out, in fact, that the movement of water influences the force of gravity. So this is the gravity anomaly of Texas. If you just think about our state, and if you think about how much gravitational force our state exerts on things that are up in the air when their satellites are flying over the state, well, our gravity anomaly looks something like this. And this pattern here is how the gravity anomaly is changing through time, and it's measured in terms of thickness of depth of water. So all these colors, the blue colors and the red colors, represent sort of water sloshing around the world. And that was particularly relevant for us here several years ago. We had a really severe drought. It was really stressful in 2011. Suddenly we lost about 100 cubic kilometers of water. 100 cubic kilometers of water that's the Lake Geneva. I mean, it's a huge volume of water. Just went somewhere, disappeared. And the Texas Water Development Board keeps a track of our surface water reservoirs. There's 119 of them, and they add up the total volume. And you can see the red track is the gravity anomaly, and the blue track is the reservoir levels in our state. And you can see they're almost the same line. So this says that our reservoirs are one huge system. We lost here 9 cubic kilometres of water out of our reservoir system. But overall, we lost 100 cubic kilometres. So most of the drought, there's been a lot of talk about drought in Texas here recently, but most of this drought involved water that was in the soil and the subsurface system. So although it may seem amazing, there really is a big scale there out in the sky that's measuring the force of the Earth. And it's demonstrating these effects that not only is the geoid varying in space, it's also varying in time. So in order to have some standard measures of where we are, these are called vertical Earth datums. And the older one was called the National Geodetic Vertical Datum of 1929, and the newer one is called the North American Vertical Datum of 1988. And these are charts that take into account the gravity anomaly, and they try using gravitational mapping to make that as accurate as they can. And there's a procedure here called VertCon, which actually is not an ArcGIS, that can be used to adjust from one to the other. And Dr. Tarberton did an exercise with that on the Great Salt Lake region. Do you want to talk about that, David?
Sure. So we had to, I was concerned with the volume of water in the Great Salt Lake, and as the students here know, and maybe the students in Texas just learning, the Great Salt Lake level goes up and down with climate, and right now it's at one of its lowest levels. And it turns out that the National Elevation Data Set that we got, the digital elevation model that represented the bathymetry, was in the North American Vertical Datum of 88, but the Great Salt Lake level had been recorded from many years ago and was using the NGVD 29 datum. So to be able to use the water level as recorded at the water level recorders together with the digital elevation model to calculate the volume, we had to account for the differences. And I was really surprised that it's up to about 0.1 meters. In other words, there's a sort of 4-inch difference in where the level of the water is depending on which datum. And even more surprising was the fact that it was variable over the sort of short distances associated with the scale of the lake. And as you get the mountains to the east, you see the gravity anomalies because there's a large masses of rock there.
Yes, this is a, yeah, you can see it gets to be a pretty subtle thing. I mean, how much gravity force depends on how much rocks you have. We have sediment being deposited, for example, at the mouth of the Mississippi River. There's more and more mass being concentrated there, so that's a gravity anomaly that gets produced by that. So it's a very interesting subject, actually. I find it quite fascinating. This is a map that I asked the National Geodetic Survey to prepare, and the question that was, how significant is this difference between these two vertical datums nationally? I mean, if you're plotting flood maps, does this difference in geodetic datum matter? It turns out that in the centre of the country, the two vertical datums are nearly the same. But once you come out towards the coasts, it's kind of like they're going like this. So here there's about a metre difference in the west and about 30 centimetres the other way in the east. And so less so in Utah and so on where David is. So you can say that the orthometric datum shifts are relevant to the base flood elevation, and so standardization on the North American datum of 1988 is justified. That was the question that we were facing. So we talked in the first lecture about map projections, the transformation of the curved Earth onto a flat map, about the idea of going from an Earth to a globe, from a globe to a flat map, and the distortions and changes that are associated with that. And important in that is the concept that we've got a certain location on the Earth, which is located with coordinates phi and lambda, becomes a location on a map with coordinates x and y, and those coordinates have reference to a particular origin, 0, 0, or a false easting and a false northing, as you'll come to see. And there are three different kinds of map projections that can be used: a conic projection, a cylindrical projection, and an azimuthal projection. Conic projections involve putting a cone over the Earth that touches the Earth actually in two locations where it cuts through the Earth's surface. And those are good for east-west areas. Texas is good, well represented by conical projections. Cylindrical projections are where you take a cylinder and you lay it over the Earth, and you touch the Earth on one line, which is where the cylinder and the Earth coincide. And that's good for north-south areas. California, for example, is well represented by a conical projection. And then there's azimuthal projections are a flat plane, and they're good for global views. The picture that I showed you from the North Pole was done using an azimuthal projection. So conical projections are of this kind, where they either touch the Earth at one location, but generally at two, where you've got a central meridian down the middle where it's the reference location. You've got two parallels where the Earth cuts, the projection cuts the Earth, or the cone cuts the Earth, and those define the parameters of the projection. These are cylindrical projections, and the one that we're going to be concerned with is the transverse Mercator projection, which is this one here. There's a cylinder that touches the Earth on a vertical line, and these are azimuthal projections, which are on a plane, and you can have them polar, equatorial, oblique, and so on. You just sort of look through the Earth on a flat plane. Now, we're going to ask some questions on the quiz and in the homework about how to interpret projection parameters so that you know what's going on here. So this is the Albers equal area projection, and it has the rather interesting property that if you take the map distance divided by the globe distance, that the distortion along the meridians is just the inverse of the distortion on the parallels. And what that means is that when you multiply the distortions together, k times 1 over k cancels out. And so the area is preserved correctly, even though the distances on meridians and parallels are distorted a little bit here. So k times 1 over k preserves area. So in this particular instance, we've got a cone that's been placed over the Earth. It cuts the Earth at two latitudes, which are standard parallels here, 29.5 north and 45.5 north. It's flattened out. That's why these blue lines kind of come out in a fan shape here. There's a central meridian for this projection, which is minus 96 degrees, which means the reference location is on that meridian. And there's a reference latitude, which is 37.5 degrees. That means that that's the 0, 0 of the latitude and longitude that are associated with this projection, and in the projected coordinate system, those are 0, 0. So that's a USGS, a standard USGS projection for North America. Now, this is a Lambert conformal conic projection, which is the same kind of thing as for the Albers equal area projection. It doesn't have the property that the area is preserved. What instead it has the property is that the parallels and the meridians always cross each other at right angles. So in a Lambert conformal conic, that's what conformal projection means. And this has a different set of parameters than the one you just saw. This is a universal transverse Mercator projection, and it's different again. Among other things, the map looks different, but the central meridian here is minus 99, the reference latitude is 0. That means that it's 99 degrees west where the circle of the cone, the cylinder touching the Earth exists, and the reference latitude is on the equator. And we talked a little bit about this in class, about the false easting being 500,000 so as to avoid negative numbers and things like that, negative coordinates in the x direction. And this is a Lambert azimuthal equal area projection. This is the one that goes onto a flat plane. In this case, the only parameters that it has are the central meridian and the reference latitude, and that's the location that the plane touches the Earth. Now, I discussed a little bit about this Webb Mercator projection, and this is a kind of a subtle thing that's used for Esri base maps, and it was introduced by Google, and the idea is that the whole Earth is divided into 256 pixels by 256 pixels. And the way that web mapping works is that a very large stack of image maps is pre-computed, and they store it on huge disks. So when you zoom in on a computer and it goes, no, and it's all clear, that's because somebody's already done all the calculations ahead of time. So basically they'd start off with a big square like this, then you have 4 squares within that, then you have 4 squares within that, and 4 squares within that, and so on and so on and so on. And so you have more and more and more maps of increasing degrees of detail as you zoom in. And this scheme has become the standard for all forms of web mapping. And more or less an industrial standard that was evolved and became adopted by all the web mapping companies. So that's called the WGS 1984 Web Mercator. So in the exercise 1 where you said, oh, you really have to use this, this is the reason. It was because Google did it first and everybody else decided to follow it. Now, I tried to figure out just exactly how the coordinates were worked out in this projection. And what I worked out was that the coordinate that goes in the vertical direction here is actually just it's a simple calculation that just says there's an Earth radius times the number of degrees that's necessary to get up to the corner here. And I couldn't figure out how to get the calculation being done in the horizontal axis. But roughly speaking, the Google people have flattened out the Earth in this sort of square way so that even though the Earth has this asymmetry about it between the polar radius and the equatorial radius, it doesn't seem that way when you look at it on the map. So projections preserve some properties, but it's not possible to preserve all the properties simultaneously. So area is preserved by projections where the distortion in one direction is just offset by the distortion in the other direction. And that's important in what we do in water because we want to preserve mass balance. You know, this much rain produces this much runoff. Shape means that local angles are shown correctly. So I showed you in the conformal conic projection the angle between the meridians and parallels always stays at 90 degrees even if the lines themselves are being curved. Directions are shown correctly relative to the center. So I showed you a map taken from the North Pole where all the meridians sort of point out from the center. That's where the directions are preserved correctly, and the Lambert azimuthal equal area prediction does that. And finally, distance is preserved along particular lines, and some projections preserve 2 properties, but that's all. So for example, the Lambert azimuthal equal area preserves direction and also area, but you can't get beyond that. You can't preserve shape, area, direction all simultaneously. And particularly distance is hard to preserve exactly. So 2 data sets can differ in both the projection and the datum, and it's important to know both of these for every data set. So this is where subtleties start to get in. You say, oh, I've got these data and it looks like it's the same thing, but it can turn out to be different in sometimes subtle ways. So let's take a look at coordinate systems here. So one of the coordinate systems that's always been important, and actually it's becoming important more so again, is called the Universal Transverse Mercator System. And this was developed by the US military services during World War II, and it's subsequently been adopted globally. Our second system is called the State Plane Coordinate System, and it is the civilian system for defining legal boundaries. So if you have a property and you say, here is my property, then that's defined in the State Plane Coordinate System. And something that's important for us here in Texas is there's something called the Texas-centric mapping system, and that's a statewide coordinate system for our whole state. And the reason for that is that within Texas there are 5 versions of the State Plane Coordinate System depending upon where you are. So if you want to make maps of the whole state, you have to have one projection for use of that. So if we take a coordinate system and we say it's defined by a pair of orthogonal axes drawn through an origin, so we've got phi and lambda here in the phi 0 and lambda 0 in the original projection and x0, y0 in the projected domain. So phi 0, lambda 0 goes to x0, y0. So for the universal transverse Mercator projection, each zone has a central meridian that's 6 degrees wide. And these zones go from pole to pole. So we happen to be in zone 14 here. And there are 60 zones that cover the Earth from east to west. the reference latitude is the equator, so that means we're always measuring from the equator. And the X shift, Y shift in the northern hemisphere is always 500,000 0. And that's so that all the values within a zone on the universal transverse Mercator projection are measured positive with positive X values. So this is UTM zone 14. So its central meridian is 99 degrees. It covers a band from 6 degrees, 3 degrees to the left and 3 degrees to the right. So that means it covers a band from minus 96 to minus 102. In fact, these zones are labelled from, they start over here, zone 1, and then they continue from west to east. The state plane coordinate system is defined for each state in the United States. So we've got east-west states, such as Texas, use the Lamberth conformal conic projection, and north-south states like California use the transverse Mercator projection. So there's for the state plane coordinate system. As I mentioned, there are 5 different zones in Texas: north, north-central, central, south, south-central, and south. And this is sort of the standard system for local measurements because it's got the highest accuracy. It's sort of configured to be so. We looked, when we were doing exercise 1, at the spatial reference system, and there's lots of different options here. This happens to be the NAD 83 system. It's a horizontal coordinate system, and you can see it defines a semi-minor axis, 635,675.2.3 meters, semi-major axis, 637,137, 637,8137 meters. There's a inverse flattening or degree of flattening, 298.25. That defines the shape of the spheroid that's there. And there's other things that are in the spatial reference definition, which we won't worry so much about now. These are some of the options that exist for geographic and projected coordinates. You've got geographic systems that are for North America. That's the option that's shown here. We've got projected systems that are for North America. Some of the ones that we're going to use are the USA contiguous Albers equal area. That's for the contiguous United States. There's also a North American Albers, North American Albers equal area. That includes Canada as well. So that's a projection that's used on some occasions for projected coordinate systems. For vertical coordinate systems, we don't have to worry about this, but for three-dimensional data it's necessary. For the data that we're going to work with, which is terrain information for elevations, we're going to use the NAVD 88 coordinate system, so you don't need to worry too much about this. ArcGIS has a set of projection files, and they contain all of these this information in a way that's, if you know what you're looking for, you can figure it out. So, for example, this is a projection file for the geographic coordinate system of North America, and it's got North American datum 1983. Here's the spheroid being defined, the units of the degrees, and so on. If you have a projected coordinate system, you've got here contiguous Albers equal area conic USGS version, and it says that the datum is North American datum of 1983. It specifies the spheroid, so all this part is pretty much the same as what you see up here, but then below that is all this other stuff here. So this says parameter false easting 0, parameter false northing 0. That means the X false easting and false northing are 0 and 0. Parameter central meridian is minus 96. That means the line down through the middle of the projection, or let's say if you're going to cut the cone and then separate it out into two sheets of paper, or flatten it out with the center down the middle, that's the meridian. The central meridian does that. The standard parallel 1 is 29.5, and parameter standard parallel 2 is 45.5. 29.5 and 45.5 are the places where the cone cuts the earth. So where is 45.5? North. Is that in Canada? No, it's not. It's in the northern part of this country. So I think 49 or 48 is the meridian that goes between the US and Canada. So this 45.5 is a line that cuts the US in the northern part of the country. And similarly, 29 is a little bit south of it here. Where's the most southern point of the United States? At least on the continental United States. Oh, let's leave out Cuba. Yeah, we're not too much into Cuba.
Key West.
Yeah, Key West in Florida. So in other words, South Texas is south, but the bottom of Texas is actually not as far south as the bottom of Florida when you look at it on the Earth. So, yeah, we don't hold the record there. Florida does. So this line here, 29.5, means a parallel that cuts the Earth that's in the south of the country. And the idea of this is that where the Earth is, but at the place where the cone cuts the Earth, the representation of the Earth is exact. So it's exact at 45.5. It's again exact at 29.5. So in between, what's happening? What's happening to the shape of the Earth? It's getting flattened out. So we've got a curved Earth that's now been set on a cone. So what's happening to the distances on the Earth? They're being shrunk a bit, right? So if you've got a curved surface, if you've got a cone underneath the surface of the Earth, you've got two places where it's fixed, and now you're taking this curved Earth and going, and you're flattening it out a bit, so that all the distances between the two parallels are getting shrunk a little bit, and then as you go past the bottom here, 29.5, and above the top, they're getting expanded a little bit. So the standard way that the two parallels are drawn is generally 1/6 of the distance from the top of the map and 1/6 of the distance from the bottom of the map is where they're exact, and there's 2/3 in the space in the middle that's a bit squished, and 1/3 each end that gets expanded a little bit. In this instance, you'll see also the latitude of the origin is 23. That means that's actually significantly further south than we are here, so that means the numbers are going to be positive. So 23 is actually below Florida, so the longitudes of the Y values are always positive. What's the significance of the fact that the central meridian is at 96 degrees west and the false easting is 0? What does that mean when you go west of the central meridian on this projection? So here we've got false easting is 0, central meridian is 29.5. Sorry, the central meridian is minus 96 here. What does that mean when you go west of the central meridian? What will the x values be? They're negative. Yeah, they're negative. So in this particular projection, which is actually a USGS projection that's quite widely used, all the x coordinates to the left, to the west of the central meridian, are all negative. Now, for most purposes, it doesn't matter. You know, your computer knows that, and it takes that into account. That affects, among other things, the calculation that you were doing about the calculation of evaporation as a function of latitude, of longitude. Now I showed you that has to be done with a negative number. Here we've got also unit meter. That means that the map units that the data are expressed in are in meters. So Dr. Tuverton added this slide to talk about distances and projected coordinate systems. Do you want to speak to this, David?
Sure. So we saw in one of the earlier slides how to calculate distance along a line of longitude and along a line of latitude, and where the long lines of latitude you have to account for the cosine of the latitude. If you're dealing with a projected coordinate system, say for example that USGS one that we just saw on the previous slide, and you're interested in the distance, say from Logan to Austin, which we may be, that's how far this news is, or our lecture is sort of spanning that distance. You can use Pythagoras theorem in the projected coordinates that have flattened out the Earth. So that says that the length squared along the hypotenuse is equal to the x difference squared plus the y difference squared. So if you evaluate that with the square root in there and you put the different coordinates, you could calculate this distance as 1,791 kilometers. Now that's approximate because of the effects of the distortion. I think the distance will actually be a little bit longer than that because this projection, we're sort of between the two parallels. If you need to get these coordinates, there's actually a add geometry tool in ArcGIS Pro that will add the point x and the point y values to the shape. So I think one of the things that we're going to do in the exercise that we'll pass out next time is have you do a little bit of these things to calculate distances. And last year we did it between Austin and Logan. This year I was saying let's figure it out between Salt Lake City and New York. And you'll have to take the latitude and longitude, enter them into a table, do this sort of calculations by hand, assuming spherical Earth, to figure out what the sort of distances are, do the great circle calculation to see what sort of difference that makes, also assuming a spherical Earth, and then project the data by bringing it into ArcMap, plotting the points, adding the x and y coordinates, and then using this sort of formula to calculate the distance. And you'll end up with 3 different answers, all of which are approximate. So it's sort of, you learn that it's actually quite hard to measure precisely the distances. The spherical calculations, the great circle calculations are approximate because we're assuming a spherical Earth. You can actually go into ArcGIS Pro and click on one point and click on another point and ask it to give you the geodetic distance between them, and then it'll show the dotted line where the great circle route is. And I think that's probably the most accurate way that we could measure distances given the tools that we've got. And I sort of posed a hypothetical question: if you're flying from Salt Lake to New York, how much fuel you could save by following a great circle route. And I was actually surprised how small a difference it's made.
So, yeah, so these are some of the subtleties, and what we're going to do when we're going to ask you to do this starting on Thursday because you've already got something that's due on Thursday. But just to get a feel for some of the subtleties that are involved in this here. I mean, calculating distance across the Earth is a tricky sort of a business. Okay, so let's summarize then what is it that what we've been doing here. So we've got a coordinate system as a data set consists of a measurement framework such as a geographic set of coordinates or projected set of coordinates, some units of measurement, a definition of a map projection for projected coordinates, so you have to know which one you're working with, and then origin, datum and projection parameters such as the spheroid of reference, the standard parallels, the central meridian, shifts in the x and y directions and so on. That's coordinate systems are actually quite complicated things. We talked about the concept of a spatial reference of a data set that comprises the coordinate system and other things that have to do with how precise that you can associate locations on that. And so ArcGIS does projections on the fly, so it can overlay data sets that have different projections, but you can't, sometimes it's a bit misleading because you don't know that there's actually different coordinate systems there. You have to make sure they're all the same coordinate system if you want to do geoprocessing. In ArcGIS terminology, there's 2 terms that are important. One of them is called define the projection. That means I've got a data set and I know what the coordinate systems are, but it just doesn't have a PRJ file. So the define projection is the function that says, oh, these data are really this coordinate system. And then this other function which is called project, that means change the data from this projection to another projection. And so in our subsequent exercises we'll use define projection and project to be able to define coordinate systems and to change them. We've got these 2 basic coordinate systems, and I want you to sort of think about this a moment, because I think this is a really important point that is easy to kind of sort of gloss over here. We in engineering and science always talk about X, Y, and Z, and we act as if the Earth was created that way. I mean, Newton did it or something. But the real Earth isn't like that. It's this geographic coordinate system, which is the phi and lambda, and then it's got z. So phi and lambda are defined in degrees. Z is defined in meters. So z is measured this way in some system that's relative to gravity, and alpha and lambda are measured around the Earth and up and down in some system that's measured in angles, and it's a geographic or it's a spheroidal system. So the z, when we say x, y, z, we just say, oh, meter, 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 we're home. Yeah, but really it's not that. It's this thing, and it's the x and y part of it is a lot more complicated. And the mean sea level is or geoid is approximated by an ellipsoid, and that gives the datum, and the vertical distance to the geoid gives the z value. So to prepare a map, we reduce the Earth to a globe and then project it onto a flat surface. We've got these different kinds of map projections, cylindrical, conic, and azimuthal, and we've got the datum, the projection type, and the set of projection parameters. And I think that's it. Oh no, there's one more here. So we've got standard coordinate systems that use projections over zones of the Earth's surface. We've got UTM and state plane coordinate systems, and then we've got the Webb-Mercator system. Now, when we have the midterm exam, we're going to ask some questions about this kind of nomenclature. So there's a lot of words here. It's just a question. The very first thing that you need to learn when you study something like this is how to learn the vocabulary. And so this is an introduction to the vocabulary of what is really a complicated world. That some people do degrees in geodetic engineering to understand this stuff better. Okay, so I think that's it. Yes. Are there any questions? No? Any questions from Utah? Dr. Tarleton?
Any questions?
Yes.
I guess I don't have a, well, no, I don't have a question, but I also looked in ArcGIS Pro to try and see about this question of whether you could have a bar chart that would show the evaporation as we had an example right at the beginning. And I don't think you can do that in ArcGIS Pro, at least for what I was looking at. I think that's because of the way we've got the data for different months of evaporation in different columns. So I think that chart that we showed earlier was using Excel, where you've got a lot greater flexibility. So if you want to make a chart like that, probably use Excel. Okay, so yeah, the point that Dr. Tarleton is raising is that, no, he's right. Because we've got this as January, February, March, April, May, and so on as individual fields, when you make a chart in ArcGIS Pro, you have to select the things, what's going to be the X and what's going to be the Y. In this case, what we really need is a bar chart. For a bar chart, we just need one record, and we need to show all those values, so it's better to do them in Excel. That's actually, I tried to do that too, the same that he described, and I ran into the same problem. Some charting is just better done in Excel. Any other thoughts? Okay, let's declare victory then, and hey, Texas wins, right? We hope. The Utah State Aggies won too.
Did they?
Yes.
Maybe I'm doing it because I'm the one that paid the year for